Kepler's third law. That's where we left off. And we talked about it in the context of objects moving around the sun. And I showed you the ratio astronomy approach and argued that once you get used to it, you'll see it's so much easier in terms of the calculation. So this is your first chance to do so. So the question here is, an asteroid takes 2 years to orbit the sun. What is its typical distance from the sun in astronomical units? Or you can interpret that as what is its semi-major axis in astronomical units. Okay, I'll give you just a few more seconds to flesh this out for those who are just joining. Maybe about 20, 30 more seconds. Okay, let's see how we're doing. Again, you can keep submitting. We have a bunch of answers here. I'll put in a histogram. One person went really high. Maybe I'll cut it off at 10. Yeah, that's great. Most of you got the right answer. 1.6 astronomical units. Again, here it's worked out. You can just use the shorthand version. Sorry, let me show it. The shorthand version, A is equal to P to the 2/3. That's one of the two pre-solved versions I gave you. Again, as long as you're using consistent units, you can use this equation. For things going around the sun, consistent units are years and AUs. I gave you the period in years. I'm asking for the answer in AUs. And so very, very simple calculation. Where, you know, the other way of doing this, just to throw this back up from last time, you would have to convert those AUs into meters, multiply by some constant in the MKS system after cubing. That gives you an answer, you know, once you take a square root in seconds, you'd have to convert to years. That's a lot of work. This was a lot easier. So I think you'll like this new technique. And eventually it gets to a point you can just look at the equation and know the answer. And maybe not with fractional exponents, but you know, if it's like something is equal to something squared, if I double the something, then the other's 4 times as much. It's much easier. Okay, let's talk about things going around the Earth and then work one more of these problems.
I have a question really quickly.
Yeah, go ahead. It's echoey, but yeah, you have a question?
Could you just like work out that example really quickly? Like I was just like totally confused.
Sure. So I'll draw it out a little bit. We got the sun. We have an asteroid going around the sun. And the total time it takes to go around is 2 years. And I'm asking you, how far is it from the sun typically? And so we're going to use Kepler's third law, which would give us the semi-major axis. So this is our p squared equals a cubed. We're solving for a. A is p to the 2/3. And so you stick the years in here. And what will come out is the semi-major axis in AU. So you just enter 2, and you'd raise it 2 to the 2/3 in your calculator. Again, putting parentheses around the 2/3. Otherwise, you'll do 2 to the 2, which is 4, divided by 3, which is 1 1/3. I wonder if we have any of those in here. If I increase the bins, yeah, they're the ones who made the calculator errors right there. And there are probably other ways to make calculator errors, but yeah, do the in parentheses, and then you just have the answer in AU. That's this distance in astronomical units, where 1 astronomical unit is the Sun-Earth distance. It was meant to be a circle, but there's 1 AU, and so this asteroid's at, what do we get, 1.6 AU. Does that help?
Yeah, thank you. That was really helpful.
Cool. Okay. Well, let's consider the case of the Earth. It's the same deal again. I'm going to spell it out with all the steps, but as you just saw from the calculation, you don't need to do all these steps. Well, let's start with the general equation for something going around the Earth. P squared is equal to some constant. And it's a different constant. If you're going around the sun, it's one constant. Going around Jupiter, another constant. Whatever the central body is comes with its own constant. So I'll put the symbol for the Earth. The circle with the plus sign is the Earth. Circle with a dot was the sun. Times a cubed. This is the general case. Sometimes a little repetition doesn't hurt. This is what we did last time. Then we're going to have a comparison object, which for things going around the Earth, the moon is a great comparison object. So the moon goes around with an orbital period of 1 lunar month. We'll make up some units. LM means lunar month. So 1 lunar month squared. The moon has to follow this same equation. And the distance the moon is from the Earth, let's just call it an Earth-Moon distance. 1 Earth-Moon distance. Just making up units, where 1 EMD is the Earth-Moon semi-major axis. Well, then again, just like last time, we could take the ratio of these two equations, and we get period measured in lunar months squared. Constants cancel, so it's equal to the semi-major axis measured in Earth-Moon distances cubed, or again, p squared is equal to a cubed as long as you use consistent units. And for things going around the Earth, consistent units are lunar months and Earth-Moon distances. So you should be able to use the equation just the same for things going around the Earth as long as you pay attention to the units. So let's give that a try. I'm going to put up another question here. I'm going to refresh this. Okay, and so this is putting a satellite in orbit. So we're literally doing rocket science right now. So you can tell your parents, yeah, I did rocket science in class today, and it was easy, or we'll see if it's easy. So here, I'm flipping it around. I'm giving you no, I'm not flipping it around. It's pretty similar. A satellite takes 1/2 of a lunar month to orbit the Earth. So I'm giving you the orbital period. What did I give you last time? Yeah, I gave you the orbital period. I'm giving you the orbital period again in this case. So this is for a satellite, takes 1/2 a lunar month to orbit the Earth. What is its typical distance from the Earth in Earth-Moon distances? In other words, what's its semi-major axis in Earth-Moon distances? Sorry.
Answer the question.
Yep, there you go.
Is a typical distance the same thing as what's it called, the semi-major axis?
Semi-major axis, yeah.
Like the same.
That's what I mean. The orbit's pretty circular, pretty close to it, so that will give you kind of its normal distance from the sun. Technically, it's its maximum distance, but ballparkish, it's the typical distance.
All right, thanks.
I think we got up to about 65 last time, so let's see if we can approach that. Yeah, so very good. You're all almost experts in using Kepler's third law. So here's the math behind that one. Again, I gave you the period. So semi-major axis is equal to period to the 2/3. Again, as long as you're using consistent units. Since this is going around the Earth, the period is in lunar months. We said it's half a lunar month, so it's 0.5 to the 2/3. And as long as you don't make any calculator errors, that comes out at 0.63 Earth-Moon distances. So it typically orbits 63% of the way between us and the Moon. Okay, so very good. And I could, now that you're seeing how this works, I could phrase it any way I wanted to. Let me just throw one more at you. Not to do, I'll just write it here, just make it up. We have a satellite orbiting Jupiter called Juno right now. And let's say it's actually orbiting really close, but we can phrase it exactly the same way as this last one here. Suppose the satellite is orbiting at an orbital period of 1/2 of a Io month. Io is the closest large moon to Jupiter. So if it's moving at orbiting at 1/2 of an Io month, then the semi-major axis would be 1/2 to the 2/3 Jupiter Io distances. Instead of Earth Moon, Jupiter Io. So, I can set it up for any world. As long as I give a comparison object, these calculations are really easy to make. Okay. We have a little bit more math today. So we've gone through Kepler's 3 laws. And Kepler's third law, what it gives us, I'll make a few notes here. K3, Kepler's third law, it gives us the relative size of the solar system. It tells us how far the planets are spaced in astronomical units. For all the planets, we know what the orbital periods are. We just watch them go around the sky. Mercury goes around the sun quickly. Neptune takes a very long time, but we can measure all these orbital periods, calculate their distances from the sun using Kepler's third law, but they're all in astronomical units. We know the relative spacing, but all in sun-Earth distances, the astronomical unit. And that doesn't tell us if the solar system is big or small until we know how big the astronomical unit is. For that, we call that the absolute size of the solar system. We don't know that until we know how big one astronomical unit is. So we're going to just do an aside here and talk about 2 methods for measuring the astronomical unit. I'll just write them down. There are 2 ways to do this. One way involves parallax. So we're going to do some parallax calculations now. We talked about parallax before, but now I'm going to show you how to calculate it. Parallax to Venus, in the case we'll do when it's at closest approach to Earth. And the other way, which of course gives the same answer, 1 AU is 1 AU no matter how you measure it, a more modern way is radar ranging. Parallax is used to measure distances, so we can measure the distance to Venus in that way, but partway through the 20th century, we could do it by just bouncing radio waves off of Venus and timing them. So 2 ways to do it. And the parallax method, we'll work through it, and you'll see something very similar in Lab 4 if you're in the lab course. The radar ranging method, I'll also work through it, and just keep those notes because you'll see something very similar at the beginning of homework 5. So you'll be able to use, what I show you now, you'll be able to use in those 2 places. So let's start with the parallax technique. And here's the configuration. So here's the sun, here's the Earth. Earth is 1 AU from the sun by definition. That's our semi-major axis. And Venus, again, you can calculate it with Kepler's third law. We measure its orbital period, calculate it, it's 0.73 AU. So sometimes we can be as much as 1.73 AU apart from each other, and sometimes we can be as close as the difference, which is 0.27 AU, or about 0.3. So let's consider the case when we're at closest approach. What is the distance? You know, if we can come up with some way of measuring the distance in like kilometers, for absolute size, we want like kilometers or meters or some standard that we know what it is. If we can come up with a way to do that, then we know how many kilometers are in 0.27 AU, and hence we can figure out how many kilometers are in 1 AU. So the first technique is parallax, and you're going to get the biggest parallactic shift when it's close. Now, I should say in reality, we don't do the measurement at closest approach because the sun is right there in the sky and it makes it really hard to see Venus. But that's how we'll do it today because the mathematics is much easier. Okay, so parallax. So let's go back to this figure. Imagine having telescopes on opposite sides of the Earth simultaneously take a picture of Venus. Last time we looked at this picture, it was the moon, but now let's pretend it's Venus. From one telescope, we'll see Venus over here. From another telescope, we'll see Venus over there. We compare the two images and there's a shift, simply because we're looking at Venus from a different observing point. And so this angular shift, let me write it down. It's often denoted theta. Theta is the angular shift, the full angular shift from one side to the other. And at closest approach, we've measured this with Venus and it's 1 arc minute, which in the days before a telescope, that's barely noticeable, but once you have a telescope, that's easy to measure. That's 1/60th of a degree. And with telescopes, we can easily measure shifts of a fraction of an arc second. With advanced instrumentation, they've gotten it down to like a millionth of an arc second or something crazy like that. But even with the images you're taking in the lab course, you see a fraction of an arc second, no problem. An arc minute is 60 arc seconds. So once we had a telescope, very easy to measure this angular shift. So now we want to turn it into a distance. So imagine taking this figure and rotating it onto its side. That's what we have here. And this is a geometry we're going to use over and over in all sorts of different applications in this course and in the lab course. You're going to see this geometry many times. So let's say this is Venus and here's Earth out here. Nothing's to scale, of course. I wouldn't be able to fit it on the figure nicely if it were to scale. And here we're looking from one side of Earth at Venus. Here we're looking from the other side. So Venus will appear over here or over here. And this angle is the angular shift between these two positions, theta. And theta is going to be some fraction of this full circle, 360, of course. There are 360 degrees in a circle. The angular shift is some fraction of it. Now, imagine going out to the circumference. We also know the distance between the two observing points. We call that the baseline, the distance between the two observing points. And that will be some fraction of the circumference of this giant circle that's centered on Venus, but goes through the Earth. And it's going to be the same fraction. Theta as a fraction of 360 is going to be the same fraction as this baseline as a fraction of the circumference that goes all the way around. It's like if you have pie and you cut out a piece of pie, if you take 10% of the pie by angle, you're taking 10% of the pie by as measured along the crust, as long as you draw your line straight. Okay, so you can see it up here. Theta over 360 is equal to the baseline over the circumference. Let me write down the dot cam. And let me actually get a fresh sheet of paper. This will eat up some space. So theta over 360 degrees is equal to the baseline over the circumference. And it's the circumference of this big circle centered on Venus. What's the equation for circumference of a circle? Anyone remember?
2 pi r.
2 pi r, where r is the radius. And in this case, the radius of this big circle is what?
1 AU. Or no.
0.27.
Yeah, in this case, 0.27. Or I'm just going to write it out as the distance to Venus. And to keep it a little bit general, we'll plug numbers in a second. Back to the dot cam. Instead of circumference, we could just write 2 pi distance. This applies to anything, whether it's parallax to Venus, parallax to an asteroid, to another star. With stellar parallax, the baseline is the diameter of Earth's orbit. For this kind of parallax, it's just the diameter of Earth. But all you have to do is measure the angular shift, and then you calculate the distance. So we said with Venus at closest approach, that angular shift is 1/60th of a degree. So I'm going to put in 1/60th of a degree divided by 360. And for the baseline, in this case, it's the diameter of Earth, which is 1.3 times 10 to the 4 kilometers. And when doing Earth baseline parallax calculations, I'll always give you that number. I don't expect you to remember that one. Divided by 2 pi times the distance. Again, distance is what we're trying to figure out. I'm kind of doing this backwards. I'm plugging in the numbers. Normally I'd solve for the quantity I want, but I'm plugging the numbers in first and then we'll solve. Anyway, so the angular shift is usually going to be small. It's often going to be in arc seconds, and you got to remember to convert it to degrees. Arc seconds to arc minutes to degrees. In this case, it was 1 arc minute, so it's 1/60th of a degree. You take that number, which is small, and divide by 360, it gets even smaller. The point is the degrees cancel. We get rid of those units. If you plug this into a calculator, you get 4.6 times 10 to the minus 5 dimensionless, because the units canceled out. The other side, I'll simplify it, 2 pi. If we divide that into the diameter of Earth, we get 2.1 times 10 to the 3 kilometers. Whole thing divided by the distance that we're trying to calculate. Okay? And next step, we're going to solve for distance. And we have it in the denominator here. We want to get it kind of in the numerator by itself. So let's multiply both sides by distance. And divide both sides by this number right here. 4.6 times 10 to the minus 5, 4.6 times 10 to the minus 5. This is just showing you how to solve an equation. Again, for many of you, this is old hat, but some of you, this is a healthy reminder. I did this because distance cancels out on this side, and this number cancels out on that side. So I get distance by itself, and it's going to be equal to 2.1 times 10 to the 3 kilometers divided by 4.6 times 10 to the minus 5, which if you put in a calculator, you get 4.5 times 10 to the 7 kilometers. So that's an example of how to do a parallax calculation, Earth baseline parallax in this case, and the distance to Venus at closest approach is that many kilometers. And so a little line there, example of how to do. This is a parallax example. But what we're really going for is how many kilometers in an astronomical unit. Once we set that, we've set the distance to everything in the solar system. And remember from this plot here, I've kind of rounded off because I've rounded a number of things off. And you're going to be doing a precise calculation in a few homeworks. So I'll let you do it to more decimal places. But the distance away is about 0.3 AU. So that's 0.3 AU is equal to 4.5 times 10 to the 7 kilometers. If we want to know how many kilometers in 1 AU, we just divide both sides by this 0.3. Cancel and get 1 AU equals 0.3 into that gives us 1.5 times 10 to the 8 kilometers. Sorry.
Professor Record, could you show the doc cam?
Yep. There we go. So what I wrote down is the distance is 0.3 AU is equal to that. Divided both sides by 0.3. So AU is by itself. 1 AU is equal to, do that in a calculator, you get 1.5 times 10 to the 8 kilometers. So even back, as soon as we had the invention of the telescope, we could determine how big the AU was, and hence how big the solar system is. Because using Kepler's third law, we know Mars is 1.6 AU from the sun, so 1.6 times this number. Venus, we just saw, is about 0.63, or what was it, 0.7 times of an AU, 0.7 of an AU, so 0.7 times that's the distance between the sun and Venus. For all the planets, we can now figure out their distance from the sun in kilometers. So it's an absolute scale instead of a relative scale.
And Professor Eckert, for like a tester quiz, will we be given theta or do we just make it 1/60th?
You'll be given. So it's only for Venus
Okay.
and closest approach that it was 1/60th of a degree, 1 arc minute. For most things, it's going to be smaller because they're actually, if you think about it, there's nothing that gets closer to Earth than Venus at closest approach. So that's as big as theta gets, except maybe for a nearby passing asteroid or something. But everything else in the solar system tends to be farther away, so it's going to be a smaller angular shift. And sometimes the problems you'll be given are stellar parallax, which means the baseline's not separate sides of Earth, but separate sides of Earth's orbit. And let me ask you, and this pertains to upcoming question in the homework, what's the baseline in AU if you're doing stellar parallax? Stellar parallax, so you're on opposite sides of Earth's orbit. What's the baseline between those two observations?
2 AU.
Yep. And so if it's a stellar parallax question, I'm not going to give you the baseline because it is 2 AU. It's the diameter of Earth's orbit. That one you should know. The diameter of Earth, yeah, just some number and I'll give it to you. Okay, that's one way to calculate the AU. Let me show you the other way. It goes much more quickly. This is the radar ranging technique. So this is radar ranging. And so for this, for radar ranging, we are just going to shoot some radio waves off towards Venus when it's at closest approach. They'll bounce off Venus and come back to Earth. That's how you do radar ranging. You blast off some could be anything really, but we usually use radio waves, and then you just time how long they come back. And it works because we know how fast radio waves travel. Radio waves are a form of light. They're not light that the human eye can see, but they're light, so they travel at the speed of light. So we get to use that first equation we encountered, like on day 2 of the course. Distance is speed times time. It's just like the first question in the first homework. The radio waves are going to Venus and back. So the round trip distance is 0.3 times 2. Again, I'm rounding off here. You'll do it more precisely in a later homework. The overall distance you're traveling is 0.6 AU to get there and back. Speed of light, sorry, DocCam. Speed of light is 3 times 10 to the 5 kilometers per second. Then you just wait. And if you wait a short time, it means the solar system is small and compact. If you wait a long time, it means the solar system is big. Of course, by the 20th century, when they did this, they already knew the answer from parallax. It comes out to be about 300 seconds. Seconds cancel. And you want to divide both sides by 0.6 to get AU by itself. So 1 AU is, you work it out, and of course it's the same answer, 1.5 times 10 to the 8 kilometers. So 2 ways to calculate the AU. It's an aside, but it's an important aside, and we got some experience doing parallax calculations, and you will have parallax calculations in the homework, one being Earth baseline, the other being stellar parallax, one where I give you the angular shift and want the distance, one where I give you the distance to the object and want the angular shift. So you'll work them both ways.
Professor,
Yeah.
where did you get the 300 seconds?
Oh, you measure it. So you time it. You send those radio waves out, and then you wait for them to come back. And that's how long it takes for them to come back.
Okay, thank you.
About 5 minutes.
Professor,
Yeah.
is Venus used because it's the closest?
Yeah, I'm using Venus in this. And Venus is usually used to measure the AU because it's the closest and easiest to measure, easiest to, since it's the closest, you're going to have the biggest parallax. So that makes it easier to measure. And you can have the strongest, if you're bouncing radio waves off, it would be the strongest return signature because the radio waves didn't have to go too far. So it's usually what's used. It's normally not used at closest approach because, again, at closest approach, you'll be also staring directly at the sun. But the mathematics are so much easier. I presented it that way to you. In the lab course, we actually use it over here somewhere in a more realistic example.
But other planets could be used as well, right?
Absolutely.
Okay, thank you.
Is that value for velocity? Is that like is that standard? Is that gonna be the same number every time, or does that change varied on what planet you're looking at?
That velocity is the speed of light, and it's always a constant. That's actually one of the two postulates Einstein used to create his theory of relativity. Speed of light's always constant, and that's optical light, radio light, gamma ray light, any kind of light. Radio waves are light. They all travel at that speed. And if there's one I will give it to you on exams, but if there's one constant that you do maybe want to memorize, it would be that. But I'll also give it to you in the exams. Okay,
Professor,
go ahead.
don't you have to sort of, because of like the light takes time to travel to Venus, don't you have to sort of pre-fire your radio wave to, so you have to know something about the speed that Venus is traveling?
Well, so good point, right? Well, Venus, what we do is we're not shooting just Venus. We're just sending out a big wide beam of radio. And most of it will go past Venus and some of it will hit Venus and come back. So
Okay.
we don't have to be too precise. If it was a narrow pencil beam, we would have to time it just right. Okay, next up is Newton. So we've gone through Kepler. You know, the whole point here is planetary motion. And Kepler solved it. Kepler's equations work. They are correct. So why do we have to bring another person in here? And why are we bringing Newton in? You know, on the same topic, Newton did lots of things, and we could have a whole course about the stuff Newton did. In fact, in the physics department, we do have whole courses about the stuff that Newton did. But in the context of planetary motion, the way he comes in is he explains why Kepler's laws are what they are. So you have Kepler's laws, and they're what we call empirical laws. They're different types of laws in nature. So empirical, that's what Kepler did. Empirical means it's a mathematical description that works. And according to Kepler, maybe that was just the way the universe was. Maybe those were the fundamental laws of how celestial bodies moved. But Newton thought, no, there's probably something deeper going on. So what Newton introduced is something called physical law. So empirical law, it's a W. Damn it, I'm right.
Doc Cam.
Yep. Empirical law with Kepler versus physical law introduced by Newton. So he says there's a deeper level of understanding. There are other laws that we can introduce, not just laws of motion of the planets, but laws of motion, period, that apply not just for the planets, but everything down here on Earth as well. It's actually one of his brilliant insights, because before this point, they thought there are separate laws that govern what happened on the Earth versus up in the heavens. Newton realized that it's all the same thing, something we'll come back to. So a little bit of the history here. It kind of mimics our current state of affairs. The bubonic plague came through Cambridge in 1665. And so they emptied out the universities. Sound familiar? And Newton went back to his country side estate. He was from a family of some means, and they had an estate in the country, far away from everyone else. And he just sat there and thought about stuff. It's what Newton was good at. And he assembled his laws of motion during that plague. Makes me wonder as a physicist if I'm using my modern day plague time effectively. But Newton used his very effectively and wrote the following textbook, which is the foundation of not modern physics, but in modern physics refers to things like relativity and quantum mechanics, but this was the foundation of physics from this point forward. And so it is called Philosophiae Naturalis Principia Mathematica, that's Latin. Often we just call it the Principia for short. And maybe my pronunciation isn't correct with Latin, but I know the way you read it is backwards. So if you read them backwards, it's Mathematical Principles of Natural Philosophy. Now, mathematical principles, that's easy enough to understand. That's mathematical equations that will describe natural philosophy. So what is this natural philosophy? Because nowadays when we say philosophy, it means something a little different from when they said it back then. Now, philosophy, we could probably all rack our brains and name half a dozen famous philosophers and maybe even know what some of their philosophy was. But back then there are different types of philosophy. And natural philosophy is the philosophy of the natural world. Nowadays we call that science, or if you want to be really particular about it, physics, kind of the underlying layer of science. Upon physics you can build chemistry, upon chemistry you can build biology. Physics is down here at the base level. So this is like mathematical equations that describe the physical world. That's what this means. And so this text is basically dealing with motion, Newton's laws of motion, and he has 3 of them, just like Kepler had 3 of them. So we're going to go through them, and at first they won't seem to have anything to do with the planets, but by next time we will connect them back to the planets. So let's talk about Newton's laws of motion. Here's the first one. Every body, I'll just read it. Every body, not like everybody, but every body, every object continues in a state of rest or a state of uniform motion in a straight line until it's compelled to change that state by a force acting on it. So let me just put that down in note form here. There it is in words. In note form, we have 3 things that we're considering. So this is N1, Newton's first law. First case is being at rest. Body at rest will stay at rest unless a force acts on it. That makes sense. The second is another natural state of motion is constant speed or constant velocity. Speed refers to the magnitude of your speed. Velocity is both the magnitude and the direction, if you want to know the technical difference there. But constant speed in one direction, you'll keep going in that direction, that speed, forever unless acted upon by a force. And then part C has to do with these forces acting on the bodies. So here's a figure that kind of shows that. Case A, this is a ball on a table. Case A, it's sitting there and just continues to sit there. Okay, great. Case B, and I know this sounds really kind of simple and intuitive, but actually B is pretty insightful for the day. Newton's saying that something that moves at a constant speed will keep moving at a constant speed unless acted upon by a force. And now if I roll a ball along a table, suppose I have a very, very long table, or a very long stretch of road or something, nice and flat. If I roll it, will it keep rolling forever?
No.
No. Why?
Friction.
What's friction?
A force.
Force, yes. So Newton realized enough. Go ahead. Okay. Newton realized enough to separate these things. Before Newton, people thought being at rest was the only natural state. And if you move something, it will return to the natural state. They didn't realize that constant motion is also a natural state. It just, every time we experience it in everyday life, there's a force acting on it. Imagine a low friction environment, maybe an air hockey table, a really, really long air hockey table. And you can scoot the puck along and it will just keep going at that speed. Not forever, because there's still some friction. There's air friction. The puck is running into air molecules. That's much closer to a frictionless environment. And so it goes at that speed much, much longer. Or you can imagine being in space and just chucking something. And you let go and it will go at whatever release speed you gave it in that direction forever and ever, as long as it stays away from gravitational fields, which are also sources of force. But even in that case, space does have some gas. It would occasionally run into gas molecules, and over eons of time, it would slow down. So kudos to Newton for being able to envision a scenario that you just can't test empirically, particularly back in his time. And then you have part 3 here, a force. You can change A or B if a force acts on it. Give me a simple definition of a force. A what or a what? Push or a pull. Yeah, that's
Or
pull or a push. Either order is fine. And so that's a good enough definition, pull or push, for this course. We can get more technical in other courses, but you'll have an idea of what a pull or a push feels like. Let's break it down into two types. We have instantaneous. I'll put that in quotes, because you never really have an instantaneous force. And I'll come back to that. And continuous. Instantaneous, it's like if you're playing pool, one ball hitting another, it seems like an instantaneous force. Before they touch, they're moving at constant speeds, constant directions. They touch, and then again, constant speeds in different directions. And that touch may have seemed like an instant, but if you filmed it and slowed it way down, the balls actually come into contact, they press against each other. The first few layers of molecules are compressing and rebounding. So nothing ever happens instantaneously, but it can happen over a short period of time, and we call that an instantaneous force. But the other type of force is a continuous force. Give me two examples of continuous forces. You've already given me one.
Friction.
Friction, yep.
Gravity.
Stepping on the gas.
What's that?
Stepping on the gas.
Yep.
Air resistance.
Air resistance is a type of friction.
Ah.
Yeah, stepping on the gas would be a continuous force there. You're combusting something in a continuous manner and using Newton's third law to propel you, which we'll get to shortly. But yeah, these are two good examples of continuous forces. Of course, gravity is our target. Even though we're talking about motion in general, we'll cycle back to gravity eventually. Let's go to Newton's second law. We'll see how many of these we can get through in class today. So Newton's second law, he's describing what happens when you apply a force on a body. And so just reading it here, when a force F acts on a body of mass M, produces in it an acceleration A, even though we already used that term, that letter for semi-major axis, you just have to remember based on context here, it's talking about acceleration. Yeah, so you apply a force to a mass and it produces an acceleration equal to the force divided by the mass. So the acceleration you get is F divided by M, or sometimes they solve it for F equals ma. You may have heard that phrase, force equals mass times acceleration, F equals ma before. So before we play with this concept, let's just define some of these terms, in terms of the units. So this is Newton's second law. Acceleration is force divided by mass, or force equals mass times acceleration. Maybe I'll come over here a little bit more space. First, velocity. Velocity is defined as the change in distance over the change in time. This delta sign just means change. Right, if you're going on a car trip, you travel a certain distance over a certain time. This would be your average speed, change in distance over change in time. So the units there are going to be, let's say, meters per second. Those are the MKS units. Acceleration, how's that defined? Change in what over change in what?
Change in velocity over change in time.
Right, acceleration is change in velocity over change in time. So the units there are going to be meters per second, whole thing per second, or meters per second squared. Okay? And then we have a force. A force is a mass times an acceleration. So ma. And so the units there, mass is measured in kilograms, acceleration meters per second squared. So the unit for force is a kilogram meter per second squared, which is a mouthful. So in honor of Newton, we just call that a Newton. So we measure force in newtons. Okay, let me see. I think I have an example here. Just want to make sure that's, no, the example will be with Newton's third law. So I think we have just enough time to go through Newton's third law. So tuck this away. It's just a way of calculating if you apply a force, what acceleration do we get? And that is how you're changing the at rest state or the constant state with an acceleration, change in velocity. Okay, Newton's third law. N3. And I'll put it up in words. You've heard something like this before as well. To every action, there is an equal and opposite reaction. Now, by the word action, he just means force. So for every force, there's an equal and opposite force. Often you've seen this in the context of, hey, if you screw me over, I'm going to screw you over, right? There's going to be consequences for your action. That's kind of a modern version of it. Another way to think of this is there's no such thing as a free force. You can't generate a force out of nowhere. There's always going to be something. If you make a force, whatever made it is going to have a force in the other direction. And so there's a similar phrase in economics, no such thing as a free lunch. In economics, you can't generate something of value out of nothing. There's going to be some cost to it. And so it's kind of a similar idea. So let's work an example. There it is, my first car. 1994 Ford Tempo. Not great, but got me from point A to point B. Called it the 94 FT to make it sound cooler than it really was. So in this example, imagine I'm driving along the highway. I don't have a picture of me driving along the highway because I couldn't take that picture while I was driving. So you'll just have to imagine driving along the highway. And up behind me comes this 18-wheeler, and boop, we have a little accident there, okay? So let me ask you a question. Who felt the greater force?
You did.
You did.
You.
Both of you.
I fooled you. No, I didn't feel the greater force.
All right.
Back in Newton's third law, what's it say? Equal and
Both
opposite.
felt the same force.
We
It's the
feel
same force. You felt a greater acceleration.
exactly. So we're going to factor Newton's second law back in here. We both feel the same force in opposite directions. Like I'm going to be thrown forward, the 18-wheeler will be thrown backwards. But what the difference is the acceleration. So again, writing it down, the acceleration you get from Newton's second law is the force divided by the mass. Same force, different, dot cam. Same force, different mass. The mass of my vehicle is much lower. Divide by a small number, you get a big acceleration. I get whiplash, I go to the hospital. Same force divided by the mass of the 18-wheeler, small acceleration. May not even know that he hit me. Okay, so here you're seeing how they all kind of work together, and we will make them work together to give us a universal law of gravity. One more example, and this will be our last one for the day. It's a video.
Number one, guy, watch.
Firing a cannon.
Fire! Number one, guy, watch. Fire!
Turn off the audio there. But no, this is not historic footage or anything. These are reenactors, of course. But they're firing a cannonball. The cannonball has, it's going to be the same force. The cannonball gets a force. The cannon gets a recoil force. Same force, but the cannonball is lower mass, and so it is accelerated more, and hence is thrown forward. The cannon is very massive, gets less of acceleration, so it moves backwards just a little before friction with the ground stops it. I did actually have Newton's second experiment, but maybe I'll show that at the beginning of the next class since I'm out of time. Okay, that's it, and I'll stick around for questions.
Thank you.
Thank you.
Thank
Thank you,
you.
Dr. Rickert.
Thank you.
Thank you.
Thank you.
Praise Dr.
Thank you.
Eckert.
Thank you.
Sorry, can you go through the parallax example one more time? I'm not sure I got that out the way.
Yeah, so let's see, let's go back to an appropriate figure. So yeah, we're going to calculate the distance to Venus using parallax. So we're observing parallax from different sides of the Earth, From one side, it appears to be in this part of the sky. The other side, it will appear to be slightly shifted. And this is the same figure on its side. So when you have to do parallax calculations, you don't have to go through all these steps. You can just grab this equation. I'll put it back up on the dot cam. Here it is. And so from the geometry from that figure, we see that this angle as a fraction of 360 degrees going around this circle is the same as this distance, the distance between the two telescopes, as a fraction of the circumference of this big circle centered on Venus going through the Earth. And so back to the dot cam, theta, the angular shift over 360, is equal to the baseline between the two telescopes, divided by the circumference of that big circle, which is 2 pi times the distance between us. That's the radius of that circle. That's where the equation comes from, but you'll be able to just grab the equation. I think in the math notes I have versions where it's solve for theta and solve for distance. Those are the two ways you'll use it, where you're given one and have to figure out the other, or you're given the other and have to figure out the one. The baseline will always be given or knowable from the problem. A little out of focus. I'm going to hit the focus button here. So in this particular example, I kind of went about it backwards from how I normally would. Normally I would say, okay, I know the baseline, that's the size of the Earth, because the telescopes are on opposite sides of the Earth. And I know the angular shift, that's the parallax shift that was measured 1/60th of a degree when Venus is at closest approach. So normally I would solve this for distance and then plug everything in. But for whatever reason, I plugged everything in first and then solved for distance and got this number here.
All right.
Okay?
Thank you.
Sure. Okay, so I ran out of time and forgot to show my demo for Newton's second law, force is mass times acceleration. And so let me just do that right now, even though all the students are gone, and I'll tack it on to the video. So this is what we'll see. I don't have a big enough space to do it here in my office, so we'll watch the video of me doing it previously in the classroom. But this is what I'm holding in the video. It's a fan car. I can turn it on, and the fan starts spinning, pushing the air, and it generates a constant force. And then the fan car has a certain mass, and so given that force and given that mass, we'll have an acceleration. Then what I'll do in the video is I'll add additional masses to it, kilogram masses, one at a time. Okay, so I'm going to play it now.
But the fan car has a particular mass. It generates a constant force. It's pushing that air through at a constant rate. It's generating a constant force. It has a particular mass, so together we get particular acceleration. We've done this once, I'll just do it again. Go faster, and faster, and faster, and faster. I almost always drop it or get my finger stuck in it, so I'm hoping for the best here. Okay, I just put a 1 kilogram weight on the car. It should move slower. The car is probably about a kilogram too, so now I've kind of doubled the mass. It should accelerate half as quickly, or half as fast. So, do you all agree this is a slower acceleration? Okay. And just to drive the point home, I'll put another kilogram on top of it. And so this should slow it down again. Okay, so it is accelerating, sort of, very slowly. I think frictional forces have overcome here, so this is not a friction-free experiment, so it kind of messed with our experiment here, but you get the idea. The acceleration is so low it could not overcome the force of friction. Or maybe the table is tipped.
missed my classroom because it would do that consistently every single time. So I got to use that same joke every single time. But there, now you've seen it.